All right, thank you for coming. Happy Tuesday. Today's a bit of a chill day. We're going to go through the lesson 3 and just try and understand what it's doing here. There's a lot of charts and stuff, and there's not really any exercises, so that I've removed like the submission option from the assignment in Canvas just because there's not much for you to do. But we're at least going to go through it and try and see what it gives us and try and understand it. We're also going to go over the project, and I've got time reserved for you to talk with your peers. I know a fair amount of them aren't here in person today. So maybe because I know the homework is individual too, and I don't think anyone submitted that yet. So maybe we have time to work on the homework and ask questions and work together as needed. That's kind of the plan for today. Yeah, question. For the project, the groups are between 1 and 3. So you can work on it by yourself if you want to, but it's easier with a group. And so I say group up to size 3. Okay. I've got an announcement. There's a talk tomorrow. Where is it? Here it is. There's a colloquium that gets put on by more typically the math side, but this one is all about the mathematics of language and learning. So there's a linguist who is coming and talking about, yeah, like the crossover between language and math, and maybe talks about language models, so maybe some AI as well. So that should be really cool. I'm planning on going. That is tomorrow at 1:30 in 201 in Galileo, which is that big lecture hall upstairs. Okay, I also just want to touch on the plan for the rest of the semester, just so you kind of know what we're working with. Today we're going to go over the charts, the last code notebook that we're doing. Thursday we're going to do trees. Um, eh, so we will do trees on Thursday. I'm hoping to get it just all done in one day. So we're going to look at a few properties, do a few problems, and we'll have the packet. I think it's going to be like 5 or 6 questions, and that's it. So that's the plan for trees, because then we're going to go into algorithms. So if you're in 374, there's going to be some crossover for that week. We will look at some other algorithms that 374 doesn't get to. But if you're in 374, you can help out the others. Then we'll look at algorithms for planarity and graph coloring, which I think is really cool. I think those are always really useful. And then depending on how long that takes, things might shift around a bit. But I'm hoping to have a few days to talk about really hard problems, like what is NP or NP complete problems and why are they hard? So that's my hope. And then the last week of the semester, I'm planning to have at least one day for project presentations and the other to just review for the final. So depending on how long the project presentations take, it may shift, but that's the plan. And just to remind you, the final exam is on the Thursday of finals week at bright and early 8 a.m. So that's our scheduled time. No one's happy about an 8 a.m. final, but alas, that is where we have been placed. So double check that you don't have flights or trips scheduled, because that's when it is. All right, sounds good. Any questions so far? All right, let's look at this notion of centrality. Okay, so I came up with a few extra slides just to help orient you to what we're talking about. So what lesson 3 talks about is something called centrality, which is this notion of how do we find the most important node of a network. And so this idea of most important node can kind of vary depending on what kind of data you're working with. So maybe you're looking at what's the highest degree node. Like maybe in a social network, the person with the most friends is the most important. Maybe it's something else. So maybe it's, so have some descriptions here where maybe it's like we look at the shortest paths through the graphs and see like what's the length of those, what people are typically in those shortest paths. And so we look at that and see like the nodes that are most frequently in these shortest paths would tend to be maybe the most important. So the way that we say most important really depends. And this is where we really get into like social networks or something like game theory. And so we won't go too much into it because it more like this topic is kind of situated in those applications. So if you're interested in that, I encourage you to look more into that. We'll kind of just see the broad overview. Okay, so there's some ways of calculating centrality. So the one that um the notebook talks about is betweenness centrality, which yeah, so, whoa. Scrolled all the way up there. So if you look at the centrality Wikipedia page, you can see that there's all sorts of different calculations. So you could look at like degree centrality, and there's equations for how do you want to calculate that. And that's partly what networks does, is it has these functions so you can run it, calculate it on your graph and say, this is the number. So betweenness centrality is all about the number of times a node acts as a bridge along the shortest path between two other nodes. So that's, if you look at any pair, if there's one vertex that seems to be repeating and most common, then we would say that that's a very important node because we're going through that a lot of the times to get from one node to the other. And so they've got this algorithm here and an equation to represent that. So again, we're not going to go into too much detail over it, just so that you know that this is a thing that we can do on a graph. We can say, what's this number? There's also closeness centrality, which is looking at the average length of the shortest path between one node and all the other nodes. So if you find here's the shortest path from one to all the other, and then you average those lengths, then you get closeness centrality. So it's a number that means something for our graph. And so being able to understand here's what it's calculating is important. So we'll see it in use. The other thing we'll talk about in this lesson is robustness, which is the idea where if we remove some thing from the graph, so if we remove these vertices and we had this property, does the property still hold? This is a common thing in graph theory, where if we say that the graph has this property, like maybe it's Eulerian or Hamiltonian, and we remove some edges, does it still hold? Or if we remove some vertices, is it still that property? And so the other question we can ask is, how many nodes do we have to remove before we don't get there? And so these are asking two slightly different questions. So one of which is, if we remove this node, does it still hold? And the other question is, how many do we have to remove before we get there? And so this graph that we'll see is kind of doing the second question, where we've got, we'll see random failure, which is where we're just kind of randomly picking this node to remove. But then the other is where we choose these like high degree nodes and we target those. And then we see that the property kind of falls drastically. So we're going to see this idea of robustness. Okay. So let's pull this up. Okay, let's go up to the top. All right, so I'm in my virtual environment. Let's go through here. Let me restart. Okay, so there's a data set with the Enron executive email graph. Let's see if we can see what it looks like. So Enron executive email graph. So I guess this is just emails between executives, and it's just a list of edges, right? It's a list of, so each vertex is a number, and so it's just, here's a list of edges. So this is a way that you could have your graph to import it. So that's what the data set looks like. I was testing this earlier, and you probably have the nx.info. I don't think that works anymore with the new version of NX. What you can do is just print the graph. So if we run that, we get this description of the graph has 143 nodes and 623 edges, which is what we would do if we ran that. And then we can just see that we've got some offshoots over here, but there's in general a big mass in the middle. This is a caveat that it assumes that the vertex names are strings. So that's why it has over here node type equals int. In case we wanted to refer to them by the integer reference, because these are all numbers. Okay, so we're gonna find what's the maximum degree. And so this is just to remind you how the max function works in Python, where if we say max of a list, it'll go through and find the maximum value. But if we run max on a list of strings, then it gives us grape, but that's because default, when we look at a list of strings, it's going to look at the lexicographic order, so like the dictionary order. And apple starts with A, carrot starts with C, grape starts with G. Let's try what? Trying to think of a fruit late in the alphabet. Watermelon would show up later, so that would give us the last, the greatest lexicographic word. So if we didn't want that and we wanted to find like what's the maximum length of all of these words, we could either write a for loop or we could use this key for the max function to say, I want to find what's the maximum value here, but according to the length. So if we do that, then it gives carrot, I think. Let's try dragon fruit. That looks longest. So that would give us dragon fruit because that's the longest word. Okay, so we can apply that to the graph where we say, I want to find the maximum node, but according to what? According to the degree. So that's going to give me the highest degree node. And that node is 105. So that's not telling me the actual degree. It's just telling me here's what the node is. And so if we want to actually find the degree of that node, it's 42. So the node 105 has degree 42. That's what it tells us. Okay, so now we'll use the centrality measure. And so that lives in nx.centrality. And specifically, the lesson chooses to go with betweenness centrality. And so this is going to give us I believe, a dictionary. And so we get the maximum value of among all the nodes, say which one has the highest centrality. And in this case, it is also 105. So before we saw that the highest degree is 105. And so by betweenness centrality, it gives us the same thing. Depending on the measure of centrality, it may not have given us the same thing, but in this case it did. And so then to find the actual number associated with that, since we have betweenness stored as a dictionary, we do betweenness square brackets, the highest, and that gives us a betweenness of 0.194, and so on. I have this commented out because if we run this, it gives us an error because betweenness is a dictionary. And so the way we get around that is it uses betweenness.get. And so that gets the actual values as we go through the list. So Max can do that work. Okay, so that finds the most central node in the network. This might be useful for your project or for your homework, to be able to say this node is most important. But now we kind of look at what's going on for all the nodes in the graph. So we can get the degree sequence. So that's using list comprehension where we say, what's the degree of this node for all nodes in the graph? Let's print that just for fun. That's going to be very long. Typically we like to have the degree sequence sorted. So let's try that. So lots of ones, lots of twos, lots of threes. Until we get up to 17, 18, 19, 20, 23, 30, 42. So we have maybe a lot of emails just like people who just sent like 1 or 2 emails or maybe less than 20. But then we get like the people who sent 30 and 42 emails. So we would see that maybe those are maybe the more important people in this graph that we want to look at. We can have some elementary statistics for that. So we can find the mean and the median, which can be useful to say the average number of emails that were sent was around 8 or 9, and the median is around 8, so median being the middle. So that makes sense. And so we can also do that with betweenness. So not just with degree, but also with that betweenness measure. So if we do that, then the mean is 0.013 and the median is 0.003. So it kind of, let's see what our old value was. 0.19. So that's significantly higher than the mean and median, which is interesting to know. All right, so then it goes into plotting it. So let's see, can we visualize this? We've got all this data. So this uses the collections package to count, like if we've got this degree sequence, how many have degree 2 or degree 9 or degree 11? So this counts how many. So the key is the degree value or the degree amount, and the value is how many nodes have that degree. So if we run that, we get this very long list where we say there's 16 vertices with degree 2. Then there's, it's not exactly sorted. Let's see if we can sort it. Nope, that doesn't work. But you see near the end where we only had like 23, 30, and 42, there was only one of them. And so we can see that here as well. Okay, so from that we can get the min and max. So we can find what's the, of the keys, so the number on the left-hand side, what's the minimum and what's the maximum? And we know that should be what, 1 and 42, right? Those are the minimum and max degree. And then we can say, okay, that's going to be my range on the x-axis. So I want to see what's the degree ranging from 1 all the way up to the end. So we can run that and nothing happens because we haven't done anything with it yet. And then for the y-axis, we're saying that it's going to be the other side of the dictionary. So that's going to be the values. So the number of nodes that have this degree. And then this is why we import matplotlib, which is, let's just do a bar chart of, so the x-axis is the degree and the y-axis is how many nodes have this degree. And so we can see that like there's a fair amount of 2s, fair amount of, what is this, probably 9s. And then as we get to higher and higher degrees, there's, that would be 23, that's 30, and that's 42 with only 1. So we can visualize it like this. So we can also do binning, which kind of takes this and converts it, or we do binning for the betweenness, because that's like each node is probably going to have a different betweenness. And so we want to say like, for this range, this is how many nodes are there. For this range, how many? Just because for betweenness, we're looking at a decimal value and not an integer value like we did with degree. And so this does a histogram where we say, here's the sequence of the betweenness. Let's print that just to see. That is. Okay. So this is the, it's a bunch of numbers, right? So this is the betweenness for each node. And so we put that in there and we say, I want 10 bins, and we execute that. This is what we get. So a lot between, or between 0 and before 0.025, At around 0.025, we have less and it decreases from there. So we have a lot with little betweenness and very few with higher betweenness. Let's try. What if we did 5 bins? Think the lower end got bigger. If we do 15 bins, then we can kind of see it more stratified. So you can play around with the number of bins and how you want it to, how fine you want your histogram to be. And so then from histograms, you get the counts, the bins, and the patches. And so you can look at those if you want. So how many are in this bin? So in the first bin, it's 106. And the last one is just 1. So we can investigate that data as much as we want. All right, then it's robustness. So first we look at the connecting components, and remember we just get the generator object. But we want to find like what's the biggest connected component. And so we'll do that with max and the key. And we find this connected component goes from vertex 1 to 3, 4, 5, and so on, up to 143. And so the number of nodes in that component is 143. Is it the length of the graph? I think so. So yeah, maybe it would help if I use the right functions. Okay, so yeah, so the graph is all one big connected component. And so we find that when we also say, give me the length of the components, and there's just one, so there's just one connected component, so the graph is connected. And so then it goes through this thing of we're going to remove some stuff. We're going to try and take apart the graph and see at what point does this property break. And so they're like, okay, let's make a copy first and work on the copy so we don't disrupt the original. And so then they choose at random, like let's choose 2 nodes at random from our list and then remove those. So this is random sample. Random sample takes the population first, which is our list of nodes, and then the K, which is how many are we gonna pick out, and then we remove those ones. So we do that, nothing happens. And then we're gonna do this repeatedly. So maybe we do this 25 times. And so then we need to figure out how many nodes are we gonna remove at this step. And so it turns out to be 5. So we'll remove 5 nodes at a time and see at what point does this break. Okay, so n is the number of nodes. We copy the graph just to be sure. We've got the proportions here. And the proportion is how many things are in this biggest connected components divided by the total number of nodes in the graph. And then we keep doing that and we'll keep removing things every time. Okay, so we do that, and then we run this to get our graph, and we can see that the proportion, so initially all of the nodes are in that connected component, but as we remove, it is fairly linear. Maybe there's a small dip here and a faster dip here, and then it kind of maybe starts to level out as we get to the bottom. So that's the random failure. So if we choose things at random, how soon is it before the node proportion just tanks? So for this, it's fairly linear. So let's try targeted. And so in this here, we're not going to randomly sample things. We're going to choose the most important ones that we saw before. So we sort it by degree. So reverse true says, let's list the highest degree nodes first. And then we get the first 5. So the :M says, give me the first 5 of that list. And we're going to remove those ones first. And so then it's fairly the same loop as before, where we're still recording what's this proportion, and then we're still removing things each time. And so let's see what the graph looks like then. So this maybe starts off similarly. We go down to maybe 0.8, and then it drops fairly drastically. So you can see after we remove maybe 30 of the highest degree nodes, then we get very low proportions. And so you can do it both on the same graph and kind of see this difference immediately. So this is a good piece, being able to say this about the graph. If we're looking at a property, maybe consider this for your project, where if you are looking at the property, see what it takes to break it, and then say, what does that tell you about the graph? So removing the first 30 or 40 nodes in the graph is really significant. And so those 30 are maybe more important. Okay, any questions on this one? Cool. Okay, so I hope that was helpful and helps you think about things. I will note that there are, if you go into the tutorials, there's other tutorials, one of which looks at like the Twitter API. I don't know. This was published in 2020, so there may be a chance that it doesn't work anymore because things have happened at Twitter. But if you're interested, it may be worth a shot to just run through it. There's also different specifically network algorithms to check out. Yeah, clustering algorithms, partitions. Let's see, we got this one. And then simulations. So if you're interested in that, go look at those. But yeah, so we'll call it good for that. All right, so now we get to go over the project, which I'm actually really excited about. Let me move Zoom out of the way. All right, let me tell you, there's a new module in Canvas all the way at the bottom. It's about the project. And so the top level assignment, that's for your final submission. And then the indented assignments, those are for our intermediate deliverables. So yeah, so we'll go through all of this. These are all described in the project. Okay, So the structure of this is roughly similar to your homework assignment. Just add another level. So you're going to so you can find some data or create the graph on your own. Although I may not recommend this based on the size requirements. But you can if you want. So you're going to find a graph and then look at its properties, run some algorithms on it, and then say some things about it. So what does this mean? You did some analysis. How does that help us? You can work in groups. You can work alone if you want, or in a group of up to 3. So the first step is due by next class, by Thursday, of make your group. And so either you go to the People tab in Canvas and make a group and give yourself a team name, or if you want me to do it, send me an email saying this is who is in my group and I'll do it for you. So that's due by Thursday. The next step is to find your graph. So I want you to start working on this as soon as you can. So my requirement is by this Friday that you at least give me some information about what you're thinking. Maybe you can put multiple if you want, if you're still kind of deciding, but get going as soon as you can and give me the idea of what your graph is going to be. The idea here is to prioritize complexity. So my requirement here is to come up with a data set of more than 50 nodes, which you could look in the Cambridge data sets, or you can go and find something other than that. You could Google graph data sets and pick the one that seems most interesting to you. But my requirement is greater than 50 nodes. Or if you want to, remember we talked about like the signed graphs, which even though they're fairly small, they impart a good deal of information. So if you want to do something like that, which is much more condensed, but still is very complex to read and understand, then I'm happy to allow that. If you've got a bigger group, then the graph has to be bigger because there's more analysis to be done. If your group is smaller or you're working by yourself, then the graph can be a little bit smaller. So I say that it may be subject to change, but your initial idea is due by this Friday. And so let's pull that one up. So for that one, I'm looking for maybe a paragraph of this is my source. You can include the link if you found it online, or just describe it. What does a sample row of it look like? So maybe it's like the Enron graph where it's just vertices. But as we're looking at an application, I would like to know what are the vertices. So maybe for the Enron graph, it would be people. For the airline graph, it would be airports. And the edges are whether or not there's a flight between this airport and back. Where for the email graph, one person emailed another. So having that written down in words is what I would like. And then just to get you started on thinking for your analysis, kind of what we did for the tour de graphs of what questions can you ask about this graph? What problems would asking these questions solve? So write that up, and then part of the project is having a paper. And so if you put more effort into this, then you can just copy paste it into the paper. If you want to put less effort into this now, that's okay. But then you just refine that and put it in the paper later. Okay, so this is due by Friday. So step 3 is load it in code with networks, or if you want to choose another library, feel free to do that. And this one is the most open-ended because I don't necessarily know what properties make the most sense for your graph. So you choose some and tell me what they are and execute some algorithms on it. We'll talk about some algorithms in the next couple of weeks, but you should feel free to go to the network's documentation, see what algorithms there are, Google them, see what they do, and then use them. If you put your code on GitHub, I'll give you an extra 5 points. And then here's where we have some progress reports. So those are due next Friday and the Friday after that. And that's just a paragraph of, tell me what you did this week. Tell me how it's going. So that's the idea for those, are to make you keep working and not just leave it all to the last minute. And then the final code, so you can still be making changes, even though we'll do class presentations, you can still be making changes as needed up until the Friday before finals week. So that's step 3, which is to write the code. Step 4 is to write a paper, a short paper about the graph, the properties, and the algorithms. And so it should be at least 1 to 2 pages. And this, these 2 bullet points are explained by that. What is your graph? What did you choose? And so prioritize here writing in, so like it should be a balance between technical writing and being able to express it in like plain English. And so we'll have a rough draft due for the week before so that I can kind of help you with that and tweak it. Also, as you go, feel free to take it to the writing center and have them see, like, can you understand this if I explain maybe these few things to you about what I'm talking about, but otherwise is understandable. Yeah, so the other aspects are, what properties did you pick? What do they mean for the graph? So this is where I would like you to say in words, where like, if we did this whole betweenness idea for the airports, maybe we're looking at the biggest hub airport. So this is the airport that gets the most traffic. And that's the property, that's what it means for the graph. And again, algorithms. So we'll choose an algorithm and say, this is what it gives me, this is the information, this is why it's important and useful. And then some conclusion paragraph where, why does the graph matter? Why does the algorithms matter? What's the real world significance of your analysis? So there's going to be the rough draft due the week before, and then it'll be, everything's due the Friday before finals week. And then step 5 is a short presentation. Depending on how many groups we have, I will adjust the amount of time. But since we're a fairly small class, I think we'll be okay. And so the structure should be based pretty much on the essay, but not just like reading verbatim from the essay. Prioritize visuals. So maybe draw the pictures of the graph and point to it and say, this is the sort of property we're looking at. Maybe pull up subgraphs. So prioritize visuals and making it interactive, and especially talking about what are the insights, what are the questions that can be answered. Why do we want to analyze this graph? And then everything's due the Friday before finals. So I've got the rubric up here. The first few rows have 0 points just because the points are going to be stored in those assignments. But the rest of them, you can see, like, did you give me the code? Is the code looking good, easy to read? Did the properties make sense? And so on. So make sure as you're writing your code in your paper, check the rubric and make sure that it aligns with that. Okay, any questions on the project? Okay. So I want to have time. We've got maybe 25 minutes for maybe spend a few minutes talking with your neighbors. If the people that you want to be in a group with aren't here, then email them or text them and set that up. If the people you want to be in a group with are here, then go ahead and make those on Canvas. And then you spend the rest of the time brainstorming what data would you want, and you can also work on the homework as well, which is due. When is the homework due? Thursday, which is basically a smaller version of the project. So this is practice, where you find some data, draw it, find some properties, and say something about it. So the homework is a mini project. Sounds good? Cool. Go for it.